So hello everyone, this is a short review of last week. So we started with the perceptron and discussed some basic issue in learning. We discussed that you have training data available, you select a model with 3 parameters which you try to learn, and learning is defined as a cost function which should be a minimum or very small when you have good performance on your learning task. And this search is done by an optimization process, which is also called the learning rule. Um, so in the perceptron, we have inputs. So these are for every data point what we consider available data, available information, also in testing. And in the notation, we add a 0 input, which is always 1 for technical reasons, and then the real inputs go from 1 to m. So we have m real inputs, but the summation here starts with 0. And in the simple perceptron, we add up all the inputs weighted by the parameters wj, which sort of correspond to the synaptic weight in a biological interpretation. They form the function h of x, and then we simply apply a sign function to give you an output of 1 and 0, sort of deciding on a class belonging to class 1 or to class 0. This is how it looks in one dimension. So here we have examples of class -1. Here we have examples of class 1. Here's y and here's x1. There's only one input. And this h function is simply w0 plus w1x. And the point where the sign switches, the decision rule switches also from -1 to 1. So the output here is 1, here is -1. Sorry. And this defines the separating hyperplane. In this case, it's a point, simply. And yeah. And this is a two-dimensional situation. So this is the separating hyperplane where h equals 0, and these are lines where h assumes certain values, here 2 and here 4, and here -2 and -4, and everything here on the left side will be classified as this reddish class, and the one on the right side as a greenish class. Yeah, you have to be careful. There are many things which are linear here. One is h of x, which is a linear function of the input, and then the hyperplane is also a linear function or linear hyperplane. Yeah, you can consider it as a weighting machine. If you have a lot of inputs, you put weight on them. They get this weighted addition, and then as a decision rule by applying a threshold function. This is the cost function associated with the perceptron. So you sum over all misclassified samples. In the training data, you put a minus in front, and you do the product of yi times h of xi. So if they have the same sign, then they're not in the set because they're not misclassified. And if they have different signs, then this minus cancels with this minus, so there's a positive contribution to the cost function. And then we learned about how to optimize by gradient descent. So we sort of move our weights into this direction to be at the local optimum. So this is the weight space, and this is the cost function, or the cost associated with the weight, and we want to find the weight with minimum cost and have an update rule which moves the weight vector in this direction. In 2-dimension, it looks like this. You have this hyperbolic type of functions here, So this is supposed to be the minimum, and then the cost function increases in all the directions, and hopefully nicely, the W moves into the to the optimal W. The perception rule is a stochastic gradient descent rule. So you go through all data points and then through all dimensions or all weight components, and every weight is updated. So the new weight is the old weight plus eta, which is a small learning rate, times the target at this input times the corresponding input dimension. And of course, this update only happens if the data is misclassified. By this pattern-based rule, you get this a little bit stochasticity in the update, which can be considered a disadvantage, but it also has certain advantages, as we will see later in other lectures, that this helps in avoiding local optima, and typically also this pattern-based learning converges faster because you update when you go through the data and you don't have to wait to accumulate the gradient before you move in some direction. Yeah, eta should be not too small, then it converges takes a long time. If it's too fast or too large, then it might lead to instability. Yeah, so this is a linearly separable problem. You have the red class, the green class, and there are many separating hyperplanes which nicely separate these two data points. But the solution in the perceptron is not unique. Any of these things which separate these two places are okay, and the algorithm actually can end up in a lot of these different solutions. So in that sense, it's non-deterministic. This is a nonlinear classification problem, which cannot be separated by a linearly separating hyperplane, at least if you don't do a basis function transformation, which we will discuss next. And the behavior of the perceptron is even sort of unstable. This is the classical example, the XOR problem, which cannot be solved. There's no way you can put a line here which separates the green from the red. Yeah, so it's even unstable. We discussed some learning behaviors here. So here you have nice convergence cost function, and if you have non-separable problems, then you get this unstable classification performance, and the cost doesn't go to zero. Okay, so the perceptron, and then we went through some examples, there are several linear classifiers which are popular. The perceptron itself is not used that much anymore, but occasionally people use it, and it doesn't have bad performance, but mostly for convenience reasons and other reasons. And this, also particularly this behavior when the classes are not separable, and you cannot really tell a priori if they are separable. People don't want to take that risk, and so people don't use it anymore, but it's occasionally people use it, and people typically get pretty good performance. So maybe I discussed then a little bit why learning is so important, and why often rule-based approaches don't give you such a good performance. So there's some hypothesis that we use rules to explain our decisions, not to make our decisions. And here one example was that maybe the wealth of a person determines if he would be interested in buying a yacht. And so we only need this one parameter. If we know this one, we don't need anything else. So it's low dimensional. It's almost like a rule, if you want. And wealth also affects a lot of other attributes or variables, like if somebody has a car, expensive home, there's a lot of overseas vacations. And then in the data, maybe this information is not given, but you know if somebody has a car, expensive home, overseas vacation. And one way would be to try to estimate the wealth based on this data, and then use this estimate to predict the yacht, the interest in buying a yacht. But in other cases, you might not even know that this quantity exists, and you have no way of estimating it or getting good training data for this. So then maybe you just observe in your data of people who had bought a yacht and what kind of attributes they had, and you are trying to model this directly, and then suddenly you end up with a high-dimensional problem, although the inherent underlying problem was relatively low dimensional. So that's why my interpretation why pattern-based approaches are so powerful and are so important, and at least currently are working much better in practice than other approaches. Okay, so this was the lecture on the perceptron. Let's see if this works. So then we looked at a review of linear algebra, and yeah, and so hopefully it was a review for you guys. If not, you can find it in any textbook on linear algebra. So vectors are typically column vectors, just an ordered set of numbers. The transposed is the row vector. Then we need matrices, and yeah, they're ordered in this array form. And if you want to specify a particular column, we sometimes use this notation with a column, and then comma 1 means we select the first column, and here we select the first row. So first component is given, the other ones are flexible. Yeah, transpose means we exchange rows and columns. Addition is multiplication with a constant. Scalar product hopefully is well known. Matrix vector product is also quite simple, but of course it's a little bit more complicated because you have more indices to take care of. Yeah, this might be a little bit uncommon. You can also multiply a matrix from the left by a vector if it's a row vector, so the appropriate dimension. And this is an outer product, which people might not be so familiar with. But you can apply the matrix multiplication rule and exactly get this result if you take the dimension of size 1 in appropriate places. But it's essentially a matrix where single components of D and C are multiplied. So this is this way. Then the transpose of a transpose is the original matrix. 8 times the product of two matrices, and the transpose of that is the transpose of the individual matrices, but the order is exchanged. Unity matrix is a special matrix with 1 on the diagonal, and the diagonal matrix also has zeros everywhere except on the diagonal, but they're not 1. An inverse of a matrix, if it exists, you can multiply it on the left and on the right and get the unit matrix. This is applicable only for square matrices, n times n. And if the inverse exists, then you can also play with the inverse. So the inverse of A times C is the same as the inverse of C times the inverse of A, if these inverses exist. Orthogonal matrices have this property that if you multiply them by their transpose, they give you the unit matrix. Also, if you do a matrix times R transpose R, or and so in other words, the transpose is the same as the inverse in this case. And yeah, this is maybe new to some of you guys. So if you have a matrix, any dimension, you can always decompose it into 3 matrices: the U matrix, the D matrix, and the V matrix. And you write it then as U, D, V transposed. And you can look at it in a picture. So here's the X matrix. And the U matrix has orthonormal columns. And the number of rows is the number of rows of X. And diagonal matrix has this form, and V also has orthonormal columns, but we are taking here the transpose. The columns are horizontal, and this sort of has dimension. The number of diagonal terms corresponds to the smaller dimension of U or V, so in this case U is smaller, and it's ordered, they're all positive and they're ordered according to size, so the solution is unique. So you can plug any matrix in your favorite mathematical tool like MATLAB, and you will get a unique solution out. Okay, that was that. Okay, and finally, last time we also covered linear regression. So it's in a way it's simpler even than the perceptron, and sort of was discovered or evolved at the same time. Essentially, it's a linear system, so you have inputs. The inputs are multiplied by some constants and summed up, and this is the output. And as simple as it seems, this is a very important building blocks in system theory. So it's quite an important model, and due to the linearity, you can also perform a lot of interesting analysis. The cost function here is the difference between the target and the prediction, and you take the square of this, so it's a positive number, and then you sum over all data points. And you can derive stochastic gradient descent rule, which is sometimes called Adeline learning rule, where component Wj is like the old one, plus eta times the difference between the target and your prediction, times the corresponding input, so the j's input of x. So it looks formally, it looks pretty much like the perceptron rule. And you can also nicely write everything in matrix form by setting the derivatives to 0, and you get this nice results. So the least squares solution, so the weight parameter which minimizes the squared error cost function, you take the design matrix, which is the matrix of all inputs, transpose times the design matrix. You take the inverse of this expression, multiply it by x transpose times y, and this gives you the solution in one line of code in MATLAB. You don't have to do any iterations, so that's nice. Then we discussed the value of regularization, and it's sort of a golden bullet, and it always works, so you should always do it, even if the data is well behaved and your dimensions are well behaved. So you add to this expression here lambda times the identity matrix before you take the inverse. This leads to the fact that this always is a unique solution now, even if you have only a few data points, and it's regularizing the solution in a very beneficial way, and it almost always gives you better performance, unless you have extremely many data points than if you don't do it. So just do it. Okay, the effort is then you have to sort of find the lambda. We will discuss later how to do this in a systematic way. I mean, not today, but another lecture. So then I showed you how some of the effects, why regression is such a powerful thing. So the data was generated from this model. So x1, x0, x2 was not an input, x3, the weight is 0, 0, and then there was some noise on the data. So in reality, y only depends on the first input, and the true parameter should be 1, 0, 0. And then one approach is to not model everything in one regression model, but do 3 models each. So do univariate models, so that's just one input. And then you see that the prediction based on x1 is pretty truthful. It's this one over here. But since x1 and x2 are highly correlated, that's the way I generated the data, you also see a big weight here, which is okay for a prediction, because if you only know x2, you can exploit this large correlation between x1 and x2, so you can also predict y from x2. But of course, it's not a causal relation, and this is a typical example of a confounding problem. If you're interested in causality, you would get misleading results. And yeah, the weight on the third input, if you just take this one input, is slightly negative. And if you do least squares regression, you get much nicer results. So the first one stays around 1, which is the true solution. The second one gets a much smaller weight. It's slightly negative. I mean, this should be 0, this should be 1. And the third one, which is uncorrelated to x1 or x2, also gets a small negative weight. So this is already much better, and the dependency on the first component comes out much more clearly than if we do the modeling individually. And then we do the regularized solution, where we picked a very good regularization parameter, and then we almost get ground truth. So the weight on the first parameter is very close to 1, the second one is almost 0, the third one is also almost 0. So this also shows you a little bit the magic of regularization, also in improving interpretability. Of course, you have to pick the lambda in some reasonable area, so somewhere around here. And as I said, we will discuss later how this is done. Yeah, so linear regression as a perceptron is often a linear classifier and linear regression are building blocks in more complex systems. We will learn about next about basis functions, but they also occur as last layer in neural networks and deep learning, and maybe now and also in the course of the lecture you will get a deeper understanding of what their role is and how they are being used. So that comes next. So this was a review, and today we will cover basis function and approximation theory in the 2 lectures. Thank you very much.